Hi future GISPs! I'm going to teach you everything that I learned to easily pass the GISP exam so that you don't have to study the 210 websites, 1,155 book pages, 1,700 Quizlet flashcards, and 291 videos and podcasts included in the GISCI's recommended study material like I did when I passed the GISP exam. In this video, I'm going to teach you everything I learned about awareness of trends in geospatial technology. Awareness of trends in geospatial technology is the third section under the Systems Design and Management category on the GISCI's exam blueprint. Let's get started. Awareness of trends. Awareness of trends means understanding how modern technologies, software platforms, processing techniques, and data sources are shaping the future of GIS. Technology changes faster than ever, so GIS professionals must understand not only what tools exist today, but how they are evolving. Here are some strategies for staying current. GIS professionals stay updated by reading GIS blogs, attending user conferences, joining GIS organizations, monitoring job postings, and participating in training programs and webinars. Conferences like the Esri User Conference, FOSS4G, and State GIS Council meetings introduce new technologies, tools, and best practices every year. Professional organizations. Professional GIS organizations exist at every level. Local user groups provide peer support. State groups like the Maryland State Geographic Information Committee and the Delaware Geographic Data Committee coordinate statewide GIS standards. National organizations like ERISA, the American Geographical Society, and the U.S. Geological Survey provide training, certification, and industry guidance. International groups like the Open Geospatial Consortium, the International Cartographic Association, and the International Federation of Surveyors define global standards and shape how GIS systems develop worldwide. Artificial intelligence. Artificial intelligence is transforming GIS by supporting automated feature extraction, intelligent digitizing, automated geocoding, and predictive modeling. Esri's AI tools automatically create building footprints from imagery, detect vegetation health, identify burn scars after wildfires, and classify cover across entire states or countries. Machine learning. Machine learning trains algorithms on large datasets to make predictions or classify data. GIS uses machine learning to predict traffic, classify vegetation, detect anomalies in utility networks, model flood risk, and forecast environmental changes. ArcGIS supports machine learning through tools like random forest, support vector machines, and k-means clustering. Deep learning. Deep learning uses networks of neurons to identify patterns too complex for traditional methods. Deep learning models like MaskRCNN and UNet detect objects such as solar panels, swimming pools, utility poles, vehicles, ships, or damaged buildings after disasters. State departments of transportation use deep learning to detect pavement cracking, measure lane markings, and analyze roadway conditions from dash cams. AI, machine learning, and deep learning work together. AI, machine learning, and deep learning technologies are being combined. These technologies work together to support autonomous navigation, live image detection, predictive analytics, automated land cover mapping, and geospatial pattern recognition that would have been impossible to perform manually. The Internet of Things. The Internet of Things is a network of connected sensors and devices, collecting data continuously. Smart meters, traffic cameras, air quality monitors, weather stations, GPS trackers, and parking sensors all contribute real-time information to GIS. Cities like Boston, Chicago, and Los Angeles use Internet of Things to track traffic congestion, waste collection, air pollution, and street light activity in real time. Utilities use Internet of Things to detect pipe leaks, electrical outages, and equipment failures before they occur. Autonomous vehicles. Autonomous vehicles rely on GNSS, LiDAR, radar, machine learning, deep learning, and Internet of Things systems to navigate and make decisions. Waymo, Tesla, Cruise, Aurora, and other companies use high-resolution base maps and sensor fusion to safely guide vehicles. Waymo's cars collect spatial data in real time, including street geometry, curb lines, pedestrian locations, road signs, and even temporary construction areas. Google Street View vehicles capture detailed imagery and LiDAR scans that feed into Google Maps, Google Earth, and various machine learning models for map updates. GNSS advancements. GNSS accuracy continues to improve with real-time correction services like RTK, RTX, and state-run virtual reference station networks. Modern receivers like the Trimble R12i, Lucia GS18, and Elmlid reach units provide centimeter-level accuracy instantly. GNSS is used in surveying, asset management, precision agriculture, engineering design, transportation planning, and mobile workforce applications. The miniaturization of technology. Miniaturization has made powerful sensors smaller, cheaper, and more powerful. Today's iPhones include LiDAR scanners that create 3D point clouds instantly. CubeStats deployed by Planet Labs collect daily worldwide imagery. Handheld SLAM scanners build maps in minutes, and pocket-sized GNSS receivers provide sub-meter accuracy. Miniaturized sensors are accelerating Internet of Things adoption and lowering the cost of 3D data capture. Drones. Drones revolutionized field data collection. Local governments use drones for property mapping, stormwater inspections, orthomosaic creation, and disaster assessment. Agriculture uses drones with multispectral sensors for crop health monitoring. Surveyors use drone LiDAR to generate bare earth terrain models quickly and at lower cost. Public safety agencies use drones to assess wildfire damage, search and rescue operations, and post-hurricane debris fields. Mobile field data collection. Mobile field data collection tools such as ArcGIS field maps, Survey123, Fulcrum, QField, and Collector allow workers to collect georeference data in real time. Modern mobile devices combine GNSS, LiDAR, accelerometers, gyroscopes, and cameras to support asset inspections, indoor mapping, environmental monitoring, and emergency response. Cloud computing. Cloud computing supports geospatial processing, database hosting, and application deployment on remote servers. ArcGIS Online, Amazon Web Services, Microsoft Azure, and Google Cloud allow organizations to manage GIS infrastructure without maintaining physical servers. Cloud GIS supports scalability, global access, failover protection, and real-time collaboration. Real-time GIS. Real-time GIS processes sensor inputs, GPS tracking data, and live events instantly. ArcGIS GeoEvent Server, AWS Internet of Things Core, and Azure Event Hub power applications such as snowplow tracking, flood monitoring, traffic dashboards, automatic vehicle location systems, earthquake early warning tools, and wildfire detection systems. Wireless and web network expansion. High-speed networks enable data-heavy geospatial applications. 5G, fiber optics, and broadband expansions allow web maps, streamlined data, cloud-hosted imagery, and large 3D scenes to load quickly. Public safety agencies rely on these networks for live field mapping and emergency response operations. High-performance computing. High-performance computing is essential for national-scale imagery processing, scientific modeling, climate simulations, and machine learning training. GIS professionals use high-performance computing for tasks like hydro modeling, terrain analysis, viewshed calculations, satellite time series analysis, and processing billions of GPS points. Tools like ArcGIS Raster Analytics distribute processing across multiple servers to accelerate large geoprocessing jobs. Distributed file systems. Distributed file systems store data across multiple nodes to increase reliability and access speed. AWS S3, Azure Blob Storage, Google Cloud Storage, and Esri's cloud storage systems function as distributed file systems for imagery, LiDAR, and enterprise geodatabases. Organizations use distributed file systems to maintain high availability for mission-critical GIS data. Robots. Robots assist with hazardous or repetitive tasks. Boston Dynamics robots equipped with LiDAR perform automated facility scans. Agricultural robots perform precision planting, spraying, and harvesting using GNSS and sensor input. Pipeline robots inspect buried pipelines while feeding real-time data to GIS for analysis. Cobots. Cobots collaborate with human operators in navigation, agriculture, and field surveying. Marine cobots use GNSS-guided autopilot systems to steer vessels automatically based on weather and wave data. Farm cobots work alongside farmers, using spatial data to optimize planting or fertilizer distribution. Digital twins. Digital twins are virtual real-time models of physical systems. Cities like Singapore and Helsinki maintain full city-scale digital twins to plan transportation, analyze sunlight exposure, simulate flooding, track energy consumption, and manage infrastructure. Utilities use digital twins of electric grids, stormwater networks, and water pipelines for maintenance planning and asset management. ArcGIS Urban helps planners understand zoning, 3D modeling, and development impacts. Indoor mapping and indoor positioning. Indoor mapping technologies like ArcGIS Indoors, Apple IMDF, Bluetooth beacons, and Wi-Fi triangulation support routing and asset management inside buildings. Airports use indoor GIS for navigation and staff movement. Hospitals use it to track equipment, patient flow, and maintenance tasks. Universities use indoor GIS for classroom management, emergency planning, and accessibility routing. (3D GIS and reality capture). 3D GIS supports subsurface mapping, above-ground modeling, utility network analysis, disaster simulation, and emergency response. Reality capture techniques like terrestrial LiDAR, mobile LiDAR, SLAM scanners, and drone photography create highly accurate 3D models. ArcGIS Pro, ArcGIS Urban, and Esri's 3D Basemap solution visualize structures, terrain, and underground utilities in 3D. Big data in GIS. Big data GIS allows organizations to process incredibly large data sets. ArcGIS GeoAnalytics Server, Spark with GeoMesa, Google BigQuery GIS, and Microsoft Planetary Computer process billions of features or temporal snapshots. Agencies use big data GIS to analyze climate patterns, transportation systems, wildlife movement, and urban growth trends. Cloud-native data formats. Cloud-native data formats like cloud-optimized GeoTIFFs, XAR, and Parquet allow users to access massive imagery or multidimensional data without downloading entire files. The USGS, National Oceanic and Atmospheric Administrations, NASA, and Microsoft Planetary Computer distribute most new datasets as cloud-optimized formats, enabling faster analysis and lower storage costs. Vector tiles. Vector tiles allow fast, scalable map rendering across devices. Esri, Mapbox, and Google Maps all rely on vector tiles for modern base maps. Vector tiles make it possible to pan and zoom smoothly while customizing styles on the fly. WebAssembly GIS. WebAssembly allows high-performance GIS processing directly in the web browser. Tools like ArcGIS Maps SDK, Kepler GL, and browser-based point cloud viewers perform spatial analysis and visualization without installing desktop software. The Spatiotemporal Asset Catalog Standard. The Spatiotemporal Asset Catalog Standard allows organizations to index and search massive imagery archives. NASA, USGS, NOAA, AWS, and Microsoft use spatiotemporal asset catalogs to organize cloud-hosted satellite data, simplifying access for scientists and GIS analysts. Open data and open standards. Open data platforms like data.gov, the US Geo Platform, state open data portals, and OpenStreetMap provide free geospatial datasets to the public. The Open Geospatial Consortium publishes standards like WMS, WFS, and GeoPackage that ensure different GIS systems can share data easily. Blockchain for geospatial data. Blockchain provides tamper-proof verification for land records, drone images, sensor logs, and other sensitive geospatial information. Some countries are testing blockchain-based cadastral systems to secure property boundaries and legal land titles. Geospatial ethics and privacy. As GIS datasets become more detailed, GIS professionals must understand ethical and legal considerations related to geofence warrants, privacy of street-level imagery, automated surveillance, and the use of high-resolution satellite data. Regulations like GDPR influence how location data is stored, shared, and processed. The Enterprise GIS evolution. Enterprise GIS is shifting toward hybrid deployments, combining on-premises servers with cloud environments. Esri Enterprise, including ArcGIS Server, Portal, Data Store, and Web Adapters, is used by local, state, and federal agencies, utilities, and private companies to manage enterprise-wide GIS workflows. Organizations increasingly integrate ArcGIS Enterprise with AWS or Azure for scalability, high availability, load balancing, disaster recovery, and cloud-based analytics. Now you know everything I learned about awareness of trends in geospatial technology to easily pass the GISP exam. Don't forget to thumbs up and subscribe to my channel so I can keep helping people pass the GISP exam and build the rewarding careers in GIS that they deserve. You can also find everything I learned to pass the GISP exam in my book, The Ultimate GISP Exam Study Guide, available on Amazon. My study guide is a comprehensive, easily understandable, graphical, all-in-one resource for passing the exam. You can find the link to my study guide in the description below. Thanks for joining me, and congratulations in advance on passing the GISP exam.